let's continue with water temperature. And when we try to retrieve water temperature with remotely sensed data, we need to use thermal bands of remote sensors. And water can be considered as something called black body. Black body is an ideal object who absorbs and emits 100% energy. Obviously, that is not possible in the real world, but water can be considered as something that is very close to a water body, which means it absorbs most thermal energy and it emits most energy, thermal energy. So we can simply retrieve the radiant temperature of water bodies and consider that as something very close, as a parameter that is very close to true kinetic temperature. And also you need to know that you can only retrieve surface temperature of water bodies. And this is not something happening only to thermal remote sensing or water temperature retrieval. In general, remote sensing can only say surface things and retrieve surface information. You cannot use remote sensors to observe something underground or under the surface, or say a surface could be ground, right? Could be a roof, or could be something covering something else, but that's remote sensing. We can only say surface. And AVHRR and the GOES, they're very famous for thermal remote sensing and water temperature retrieval. The first one, this sensor, AVHRR, is usually carried on satellites with sun-synchronous orbits. And GOES, the first character here, G, refers to geostationary. So it's a satellite using geostationary orbit, which means it looks at a specific area on the Earth. Okay, it rotates as the Earth rotates. And AVHRR is very famous. It has 3 thermal bands, band 3, band 4, band 5. They can be used to address water temperature. And here is an example of AVHRR data. It is actually a product instead of a raw data image or a raw image. The theme here is temperature. Okay, on the right side we have this legend. So if it is warm color, yellow, orange, or even red, purple, it means that the temperature, surface temperature of the ocean is pretty high. If it is cold color, such as blue, green, or even purple, it means that the surface temperature of the ocean is low. So here is the figure. It is showing obviously the east coast of United States, and we can say the large water body here is Atlantic Ocean. And you can see that actually in the center of the ocean, the temperature is relatively high compared to the near coast water, right? Because for the near coast area, we can say the color is what? Is green, which means it's above 10 Celsius degree, below 20 Celsius degree. But in the middle of the ocean, the temperature is obviously in yellow and dark yellow. It is somewhere between 20 Celsius degree and 25 Celsius degree. Okay, I'm not an expert in ocean temperature or surface temperature, but this is a spatial pattern this image is trying to show you. Okay, so another example here, but this time it's global scale. It's at global scale. So worldwide sea surface temperature SST map derived from still AVHRR. So you can see that the spatial pattern for surface temperature, sea surface temperature here is very obvious, right? Around equator, oceans close to equator, they have relatively higher temperature. And if you go to the north or go to the south, the further you go, the lower the temperature of ocean surface. That makes sense, right? Because the equator areas close to equator, they receive most energy from the sun. And here I'm trying to show you some phenomena that are very famous. The first one is called La Nina. Second one is called El Nino. Okay, on the left side, we have the normal spatial distribution of temperature, ocean surface temperature for Pacific Ocean. It's monthly, surface temperature maps derived from in situ buoyant and remotely sensed data. On the left side, we have the normal one. So if you compare this one, the normal one, with the one showing you La Nina, what's the difference? You can see here, this is equator, right? This black line here in the middle is equator. So if you compare this area, let me use a pointer, pen, and color. Let's use green, okay? This area here and right here. You can see that when La Nina is happening, the actual temperature, ocean surface temperature within this area in the middle of Pacific Ocean, say closer to America, is lower than normal. Because here we have a yellow and orange, but on the left side is basically red. That's La Nina, okay? Abnormal low temperature in Pacific Ocean. El Nino is the opposite of La Nina. So if you, for the same area, if you compare El Nino and the normal situation, you can see that El Nino means that if El Nino phenomenon is happening, it means that the sea surface temperature of Pacific Ocean is higher than normal scenario, okay? And it is exclusively representing the situation of Pacific Ocean that is part of Pacific Ocean that is very close to South America, okay? So some, say, applications of sea surface temperature remote sensing, okay? And then besides water temperature, we can also use remotely sensed data to address precipitation of different forms and snow and ice, okay? So visible infrared techniques for precipitation estimation, that's something we usually use for precipitation, okay, visible infrared. So we can use brightness of reflected sunlight from clouds. Let me turn off the pen, okay. We can use brightness of reflected sunlight from clouds, of course, top of the clouds, to address cloud thickness. Okay, this is an indicator meaningful to climatology and meteorology. Okay, and we can also use it to estimate the likelihood of bearing rain. So it can be used to predict precipitation. Okay, and also the temperature of the top of the clouds. The colder the cloud top, the greater the likelihood of precipitation. Okay, so some products here, for example, twice daily estimates of outgoing long wave radiation on board AVHR to estimate monthly rainfall. And for GOES satellite precipitation index, GPI is an index exclusive to GOES satellite. High possibilities of raining if the cloud top temperature is lower than 235 K. This is Kelvin, okay, not Celsius or Fahrenheit. So cloud top temperature is significantly correlated with the possibility of precipitation. Okay, that's infrared. We can also use active and passive microwave techniques to address snow. Okay, microwave remote sensing is usually active remote sensing. It's not a part of optical remote sensing because the wavelengths, EMR wavelengths used by microwave remote sensing is within the range of microwave and even radio. Less radio, but mostly microwave range. So we can use high frequency scattering channels to detect the presence of precipitation, size water, and or ice particles within the clouds. So cloud is something very important for snowing, for precipitation, right? Because it is the carrier of water of different forms. Could be water vapor, could be ice particles, right? And here is a satellite mission. It's called Tropical Rainfall Marine Mission. I mean, its name tells all, right? It was launched in 1997 and it has 5 sensors for different purposes: precipitation radar, the TRMM microwave imager, okay, visible infrared scanner, lightning imaging sensor, clouds and Earth's radiant energy system. So you can say this mission is used to address precipitation, to map clouds, okay, to retrieve surface temperature, okay, with thermal bands. So let's talk about snow. So snow runoff can be both beneficial and disastrous. The beneficial part is that snow is a source of water. It is the lifeblood for most agricultural activities in semi-arid climates, which means that even a specific land lacks water, but if there is glacier nearby, there will be seasonal rivers, okay, carrying water, so you can agriculture there, you can grow things there, okay, provide much of the potable drinking water, so you can grow things, you can live there, humans can actually live there. And disastrous part, a tremendous buildup of snow or ultimately thaw can cause severe flooding, okay, or avalanche, okay, and consequently loss of life and property. So this is actually telling you the importance of snow monitoring, right? Why do we care about snow? Why do we need remotely sensed data to address the volume of snow or the movement of glacier? Because it is close to our life, to our society, okay? And how to identify snow. Okay, we can use visible infrared spectrum imagery to do that. Okay, for example, how to identify snow from other ground objects. Firstly, snow is very bright. Okay, when you are looking at a pack of snow in your life, you know it's bright. Okay, so it's very easy to identify snow from vegetation, soil, water, or other widely distributed land cover types using visible light. Okay, and also there is another problem. Clouds can be very bright if you're looking at those clouds from the sky. So how to differentiate snow from clouds? Okay, the most straightforward way is that snow doesn't move, clouds move. So you have to look at the same area continuously, or when a satellite is flying over a specific area with snow and some clouds, you have to take several pictures or even more pictures in short time to say if something is moving or something is not moving. So they can be very bright, but the moving objects, they're clouds, right? Those objects doesn't move. Those objects don't move, but still with very bright color can be snow, right? And also you can use spectral difference at mid-infrared regions to differentiate them. Okay, because this is mid-infrared, it's not about move or not move or the color or tone of the object because it's invisible, right? So here is the reflectance curve of clouds and snow. You can see that. Let me draw a threshold here. Here is the threshold for differentiating clouds and snow. On the left side, we can see that the reflectance curve of them, they're very similar to each other. But after that, okay, when we are stepping into mid-infrared range, you can see the reflectance of clouds is very high. On the other hand, I mean, snow has 2 peaks of reflectance. But if you compare this whole curve with the curve of clouds, there is huge difference, which means that invisible light, clouds and snow, they look the same. They're both bright, but in mid-infrared range, in mid-infrared area, clouds are brighter than snow, but this brighter is something you cannot see with your eyes. It is brighter to the sensors, right? Because the reflected energy from clouds is very high. On the other hand, the reflected energy from snow in mid-infrared range is very low for snow. Okay, so this is how you differentiate snow from clouds using visible and infrared imagery. Of course, you can use microwave regions to identify snow. Actually, this is actually more common in remote sensing. I have colleagues and classmates back in China. When I was in graduate school back in China, lots of my friends, they did research about glacier, about snow in China or around the world. Most of them, they use microwave remote sensing to address snow-related problems and issues. Okay, so the microwave region offers a promise for retrieving more important snow information. For example, snow depths. Actually, if you can have the depth of snow, you can calculate the size and volume of snowpack, right, or glacier, and the water content and the amount of presence of liquid water in the snowpack, which means that they can even measure the humidity of the snow. Some snow, they are very dry. Some snow, they are relatively wet. So this is something more in detail than the size of the snow, or if there is snow or not, or differentiating snow from cloud. You can calculate snow depth. You can retrieve a water content of the snow. Okay, and you can even tell if there is water in snow. So this is microwave remote sensing. Sorry, 1 second. Okay, I'm back. There was something wrong with PowerPoint. So you can say that if you are interested in, say, identifying snow and addressing glacier-related issues, or you want to carry out snow and glacier-related studies using remotely sensed data, I would recommend learn some knowledge of microwave remote sensing. Okay, because microwave remote sensing is widely used in identifying snow, identifying glacier, and other in-depth studies. And for this class, this is just an entering level remote sensing class, and it's most of the content of this class is about optical remote sensing. And usually there is another independent class for microwave remote sensing, but right now we don't have that in our department. So it's just an advice. If you are interested in water remote sensing, and more specifically, you think snow is very interesting, glacier movement and related studies, they are very interesting. They're very interesting. You want to follow, you want to do it in future in graduate school or work. I would say microwave remote sensing is more suitable. Okay. Yeah, that's all for this lecture. This is also the last lecture of the class, and thank you for your participation, virtually participation of the whole semester. And yeah, good luck. Thank you.